Hi, this is Dr. Brad Neal with the University of Indianapolis. I'd like to help you work through this problem. So the key thing about this problem is to realize what exactly is going on. So to help do that, we should probably make a picture. So if we draw that picture out first, we might say, okay, well, we've got ourselves a nice little pond here. And what we're doing is we're taking some can of oil and we're going to drop that oil right onto our pond. What's going to happen? Well, we're going to have our pond, and it's now going to be covered with oil. But let's look at it from the molecular level now, and from a perfectly straight on in viewpoint. So what that might actually look like is there's the surface of our water, so water surface, there you are, and on top of it, we have all these molecules of water. And the key part here is that in the problem it says it's a monolayer. That's a layer that is one molecule thick. So if it's one molecule thick, that gives us a lot of information. We know that the molecules aren't stacked on top of one another. We can now think about what's happening here as really a cylinder of sorts. So we could draw a cylinder like that, and well, we know that in a cylinder we have some area of that cylinder, but we also have the height of the cylinder, and that height is going to be represented by the height of each individual molecule. Okay, how's that played in with the information we're given? Well, we're also told the volume of a cylinder is, volume of a cylinder is pi r squared. So we know the volume of this cylinder is going to equal pi r squared times height. Well, height's what we're looking for. What about this pi r squared? Well, for a circle, pi r squared is equal to area. Problem gives us information about what the area is. Problem tells us the area of the surface of water is 40 meters squared. Great. So that is then 40 meters squared. Let's plug this into our original equation now with all the information we know. Okay, well, that original equation we could rewrite as saying volume equals area times height. The area was 40 meters squared. Height is what we're looking for. What about the volume? Well, volume was that 10 milliliters. So we can plug that in over here, and I really meant to say 0.10 milliliters. Cool. Well, we've got what looks like a big issue here. We've got milliliters on this side, meters square on that side. How can we get this to work out nicely for us? Because we need our units to cancel. If we follow our units, we're always going to get to the right answer. Well, let's take a look at the milliliters first. Milliliters is a nice unit of volume, but we can convert that into something that looks like a distance measurement, something that's a little bit more analogous to meters. If we remember, our 1 milliliter is equal to 1 cubic centimeter. We can use dimensional analysis to say that 1.10 milliliters is equal to, we can take that volume and we can multiply that by our conversion factor. There we go. And we end up with 0.10 centimeters cubed, because our milliliters canceled. Okay, we can rewrite our equation now as 0.10 centimeters cubed is equal to 40 meters squared times height. Well, our centimeters cubed and our meters squared still aren't in the same kind of, they're now metric. They're both measurements of that have a length built into them, but we would like the centimeters to be meters or the meters to be centimeters, one or the other. I'm going to elect to convert my meter squared into centimeter squared. So that's the next thing I'm going to do. That's the next thing I'm going to focus on, this one. So to do that, I'm going to take my 40 meters squared, and to get rid of that meter squared, I need to remember, well, for every 1 meter, I have 100 centimeters. If I cancel out units, well, I've got 1 meter down here, and I had meters squared as part of that 40. So I can't cancel out both of the meters on that meter squared, because it literally is telling me I have meters times meters. But I can cancel out one of the meters. So if I stopped right now, I would be left with units of meters times centimeters in my problem. Okay, I want it to be centimeters squared. So how can I get rid of that other meters? Well, I can say it's 1 meter times 100 centimeters again. This is useful because I can say now, well, hey, this other meter that I didn't cancel before, I can cancel here. And I'm left with centimeters and centimeters. So we can type that into our fancy-dancy calculator, and we can say our 40 times 100 times 100, and we end up with 400,000. What's our units? Centimeters squared. Great, so I can plug this information back into my original problem. So now I've got 0.10 centimeters cubed equals 400,000 centimeters squared times h. Not too shabby. Let's isolate h. We can divide both sides by 400,000 centimeters squared. Make sure you keep your units with you. You'll want to keep track of those units. That's going to help you figure out whether you're doing the problem right or wrong. In this case, it's very helpful because we can say, oh, hey, up here in the numerator, we've got centimeters cubed. In the denominator, we have centimeters squared. The centimeters squared gets completely canceled, but only 2 of the centimeters in the numerator get canceled. So I'm left with the unit of centimeters. What's that going to be? Well, if I take my 0.1, divide that by my 400,000, I end up with 2.5 times 10 to the negative 7th centimeters. So I'm done, right? Maybe not. I should check up here and I should see, oh, hey, the question is really asking for the height to be in nanometers. What's the length of the molecule in nanometers? Okay, so I need to convert this into nanometers. I always like to take the number that I've got, in this case, so that 2.5 times 10 to the negative 7 centimeters, and I like to convert that back to my base unit for whatever I'm measuring. So in this case, it's length, so the base unit would be meters. I like doing that because I know what the conversion from centimeters to meters is. I know what the conversion of meters to nanometers is. I don't really feel comfortable converting centimeters to nanometers directly all the time. So yes, if I do one additional step by converting to meters and then converting to nanometers, it is an additional step, but I know I'm going to get it right, or I've got a better chance at getting it right. So to convert that, I have to remember what my conversion factor is for centimeters to meters. Well, I've used it before in this problem. It was 100 centimeters for 1 meter. Okay, what cancels? Well, the centimeters do. Nice. I'm not going to solve the problem yet because I'm doing dimensional analysis. I'm going to go ahead and say, okay, I can convert that meter into nanometers now. So what's your conversion of meters to nanometers? It's one of those things you're supposed to know. You remember it? Here's hoping. You're looking at 10 to the 9th nanometers. Remember, it takes a lot that 10 to the ninth is a really large number of things, a lot of the small unit to equal 1 of your bigger unit. So I can now double check, make sure that I actually am done. I put the equal sign, but I should check to make sure that my units are going to work out. Okay, so I've got meters up here, I've got meters there. The only thing that I'm left with now unit-wise is nanometers. Hey, that's what I want. So far, looking so good. So we can now punch that into our calculator. Let's calculate by multiplying the entire numerator and then dividing by the entire denominator. Don't do individual math problems in between. You'll end up with rounding errors eventually and later on in the class. So we can take the 2.5 times 10, if I can find it on here, times 10 to the -7. And I can multiply that by 10 raised to the 9th. And then I can say divide that by 100. And I end up with a number of 2.5. But what are my units? That's right, it's in nanometers. So, it's kind of a bad end. Nanometers. So the height, the length of each of my oil molecules is, final answer, 2.5 nanometers. Thanks, and I hope that helped.